we started by addressing the notion of particles. Then we described the stresses, which are the forces that restore the particle to its equilibrium state after deformations. We then described the notion of particle displacement, particle velocity, particle acceleration and strains, including volumetric strain and shear strains. Next, we described the causes of these deformations, which are the changes in stiffnesses or compliances and density. Finally, we are now going to describe external forces, which cause wave propagation in the first place. Let's start by talking about external sources in the wave equations. So, how do we describe forces which can cause wave propagation in the first place? Our next task is to include the sources in the equation of wave motion and in the Hooke's law, which cause wave propagation. A stone dropped into a tank of water generated acoustic waves. A sudden disturbance at the point of impact was responsible for exciting these waves. Earthquake faulting is another example of a sudden deformation which generates seismic waves. Actually, waves are generated almost any time a sudden deformation or movement of a portion of a given medium takes place. Man-made sources of seismic waves are also used to probe the subsurface. Seismic sources can be described as forces, body force, and surface forces. The body forces are related to mass or volume. The surface forces, or contact forces, also known as traction forces, which act at the surface of the earth or at the seafloor. They reflect the pulling and pushing of atoms on one side of a surface against atoms on the other side. Surface forces are reckoned per unit area across the surface on which they act. The stress forces, which are associated with volumetric and angular deformation, can be characterized as a set of surface forces. No matter how complicated a system of seismic sources is, it can be represented by a body force that we will denote by Fi, and/or by stress distributions that we will denote by the tensor negative uppercase I, Ij. If the Earth is at rest, the sources are null. However, if one of these sources is non-null, the equations of wave motion can be modified as follows. The second equation here is known as the generalized Hooke's law because the presence of source term negative uppercase I, Ij. By substituting the generalized Hooke's law into the equations of wave motion, we arrive at the elastodynamic wave equations for the particle displacement field as follows. We have explicitly introduced the variables relative to particle positions in space and time in these equations to emphasize that the sources Fi and uppercase I, Ij, can be distributed over a volume, that is, volume source, or located at a specific point, or point source. In seismology, most sources can be treated as point sources, as we will see later. Let's repeat this due to its importance. We have explicitly introduced the variables relative to particle positions in space and time in these equations to emphasize that the sources Fi and uppercase I, Ij, can be distributed over a volume, that is, volume source, or located at a specific point, or point source. In seismology, most sources can be treated as point sources, as we will see later. We can now conclude that a seismic source can be represented by a set. This set has three characteristics. A, it determines the mechanism of the source via the non-zero elements of this set. B, it defines the pulse, which describes the magnitude, the duration, and the overall time dependency of the source. And C, it specifies spatial distributions of the source. Let's repeat this. We're now concluding that a seismic source can be represented by a set. This set has three characteristics. It determines the mechanism of the source via the non-zero elements of this set. It defines the pulse, which describes the magnitude, the duration, and the overall time dependency of the source. And it specifies spatial distributions of the source. In selecting one particular source system, such as Fk, uppercase I, Ij, one of the fundamental questions we have to address is what waves we are going to generate: P waves, S waves, or both? The answer to this question depends on the type of deformation the source system produces. If the deformation is only volumetric, then only P waves will be generated by the system of forces. In other words, when divergence of particle displacement is non-zero and the curl of the particle displacement is zero, we generate only P waves. If the deformation is only a change in shape, then only S waves will be generated by the system of forces. In other words, when divergence of particle displacement is zero and the curl of the particle displacement is non-zero, we generate only S waves. If the deformation includes both a change of volume and a change in shape, both P and S waves are generated. In other words, when divergence of particle displacement is non-zero and the curl of the particle displacement is non-zero, we generate both P and S waves. Now it's time for a quiz. Does the following stress source generate P waves, S waves, or both? The answer is only P waves are generated because we have an explosion here. In this source, are P waves, S waves, or both P and S waves generated? The answer is S waves are generated because we are dealing with zero normal strain in homogeneous isotropic media. In this final source, are P waves, S waves, or both P and S waves generated? The answer is both P and S waves are generated. For example, because the normal stresses are not equal. One of them is zero. Now let's talk about examples of external sources. This figure represents an explosive source. A charge of dynamite is fired in a shot hole, generating waves which radiate with equal strength in all directions in spite of the presence of the hole. It generates P waves in a homogeneous solid. Here is the description of system of sources. The stress source describing explosions and the body force are 0. Phi T is the source signature. Sometimes we also call the source signature a wavelet. Here is an example of pulses describing phi T. We can see that a pulse contains information about the magnitude and the time dependency of the source. Here is an example of falling weight sources. The impact a falling weight offers a means of applying a force normal to the surface. It generates P and S waves. Notice that the stresses are 0, and the vertical component of the body force is non-zero. Phi T here is the pulse of the weight drop. Here is an example of a horizontal force source. This is similar to falling weight sources, with the force parallel to the surface of the ground, which can be exercised by moving mass. It generates P and S waves. Notice that the stresses are 0, and one of the horizontal components of the body force is non-zero. Phi T here is the pulse of the weight drop. Our objective now is to discuss examples of seismic wave radiation in an unbounded non-viscous fluid and in an unbounded solid. Although these two cases are probably the simplest ones, they provide the framework for understanding the more complicated cases that we will encounter in future lectures. Let's start with seismic wave radiation in liquids. Forces in a non-viscous fluid, like water, are always oriented along the normal to the surface on which the force acts, regardless of how the elementary volume, that is, particle, is oriented in space. Based on this property, the seismic source in a non-viscous fluid can be represented as a stress source. Assuming that the seismic source is a source point, it can be described as follows, where the external stress tensor is diagonal because of the delta function and the body forces that are 0. Where IV is volume density of volume injection, phi T is the pulse of the stress source at x equals xs, and Kelvin is the bulk modulus. In practice, this system of force is achieved by a gas or water impulsive injection known as an air gun or water gun, respectively. A typical mechanical device of a water gun source used in seismic exploration at sea is shown here. It consists of two chambers, the upper firing chamber which contains compressed air, and the lower chamber, which is filled with water. When the gun is fired, the compressed air forces the shuttle downward, expelling the water from the lower chamber. Here is an example of source signatures for a water gun. Again, we can see that a source signature contains information about the magnitude and the time dependency of the source. A typical mechanical device of an airgun source used in seismic exploration at sea is shown here. It consists of an air compressor and storage tanks of compressed air, and an electrical firing circuit. When the firing command is received, the airgun releases a specified volume of high-pressure air into the water. The airgun is the most popular marine seismic source today. Here is an example of source signatures for an airgun. The first pulse is the desired sourcing signature. The second pulse is known as a bubble. The effect of this bubble is removed during the processing of seismic data. For the same reason that forces constituting the stress tensor for a non-viscous fluid are always oriented along the normal to the surface on which the force acts, the stress tensor is diagonal, and all the normal stresses are identical. And they are minus P, where P is pressure. The shear modulus is 0, and therefore the stiffness tensor is described by the bulk modulus only, as we described in the previous class. Here is the equations for wave motion in the fluid. We here use the particle velocity instead of particle displacement. Going a step further, we arrive at a single equation by combining the stress-strain relationship and the equation of wave motion. Let's now show snapshots as functions of external sources. Let's look at seismic radiation based on a numerical computation of these equations. The unbounded non-viscous fluid in this case is water, which is P wave velocity equals 1,500 meters per second, where density equals 1 gram per cubic centimeter. We here show snapshots of the wave propagation. The physical quantity displayed here is the pressure P. Notice that the amplitude of this deformation is uniformly distributed in all directions with respect to the source point. The reason for this uniform distribution of amplitude with direction is that the system of sources used in this example is invariant with direction, and that the medium under consideration is homogeneous and unbounded. Although only volumetric deformation occurs in non-viscous fluids, we are still indirectly able to measure the displacement of particle velocity by using this relation. We will discuss the practical issues related to using this relationship in future lectures. Here is the vertical and horizontal components of the particle velocity, whereas the travel time between the pressure and the particle velocity is the same. The amplitude radiation patterns, that is, the amplitude distribution with the direction of the observation point with respect to the shot point, of the components of particle velocity are different from those of the pressure data. To understand the variation of amplitude here, let's look at the radiation pattern of P waves caused by explosives. On the left are snapshots, and on the right are radiation patterns. To understand the variation patterns of the amplitudes, we simply have to take the vertical component of each vector of the radiation patterns associated with volumetric deformation. The top right figure is the radiation patterns of the volumetric deformations, and the bottom right figure describes the vertical component of each of the vectors of the radiation patterns of the volumetric deformation. For the horizontal component, we simply need to take the horizontal component of the vector of the radiation patterns of the volumetric deformation. We repeated the experiment in the previous figures with exactly the same source on an unbounded homogeneous solid. The properties of this solid are P wave velocity equaling 2,000 meters per second, S wave velocity equaling 1,000 meters per second, and density equaling 1.8 grams per cubic centimeter. The snapshots confirm that pressure sources generate only P waves, irrespective of the properties of the isotropic medium. The amplitude radiation patterns are exactly the same as those of fluids, that is, invariant with direction. Let's now consider a horizontal source in an unbounded homogeneous solid, with P wave velocity equaling 2,000 meters per second, S wave velocity equaling 1,000 meters per second, and density equaling 1.8 grams per cubic centimeter. We captured the horizontal and vertical components of particle velocity. We can see that P and S waves are generated in this case, confirming that a horizontal force produces both volumetric and angular deformations. The amplitude radiation patterns of the particle velocity are totally different from those of the explosive source. To understand the amplitude distribution in the previous slide, we simply have to take the vertical and horizontal components of vectors of P waves and S wave radiations shown here. Notice that although the source in this case generates P and S waves, we can still measure P and S waves separately by calculating the divergence of the particle displacement and curl of the particle displacement. The results are consistent with the fact that divergence of the particle displacement describes volumetric deformations, that is, P waves, and curl of the particle displacement describes shear deformations, that is, S waves. Now we will discuss geometrical spreading. Wave energy spreading outward from a disturbance as a spherical wavefront is illustrated in this picture. For each distance the wave travels, the energy must be distributed over a much larger area. Since the total energy on the ever-increasing sphere of the wavefront is constant, the energy density, or energy per unit area, must decrease as the square of the distance from the source. Consider the amount of energy distributed over a small area of the spherical wavefront at one instant, and project that area onto the wavefront at a later instant in time. Since the surface area of a sphere is 4 pi r squared, where r is the radius, the ratio of the areas must be equal to the ratios of the squares of the radii of the spherical wavefronts. Thus, energy distributed over the new area of the wavefront must decrease as 1 over distance squared, because wave amplitude is proportional to the square root of wave energy. The amplitude decreases as 1 over distance. Remember, there is a large selection of iMode education lectures, which can further enhance your knowledge of wave propagation, elasticity, electromagnetism, wave field sampling, wave field decomposition, and imaging. Thank you for listening to this iMode education lecture.